We are now interested in the analysis of the stability of closed-loop systems as a way to support the design of feedback controllers. So we're going to call this stability of closed-loop systems. So here's how it goes. So you are given a plant P. The plant P takes U as input and spits Y, some output of interest, at the output. As we have already mentioned, we assume that we read this Y and we compare it with a certain Y sub desired in such a way that the error signal is fed into some logic which is a linear controller, so we call it K, like K of S, okay, and P is P of S in the Laplace domain. That's very often how we will talk about them. And what we are interested in is the closed-loop system that consists of the box inside the dashed red box. Is the system stable? Indeed, when we close the loop, we change the dynamics of the system. And we could very possibly to destabilize the system. Therefore, running against our interests. So the way to understand this is that what we want is understand where the poles of the closed loop system we understand where they go. And for that, we need to understand what the poles of the closed loop system are. Now, we know that, so if this is y sub d, and that is y, the transfer function from y sub d to y would be equal to k times p over 1 plus k times p. Of course, I mean k is equal to k of s, and p is equal to p of s. These are two rational fractions. Now, if I write that k, and of course, so we are interested in the poles of these guys. So in order to understand what those poles are, what we can say is that we can write Kp is equal to num over den variables of S. And therefore, we can look at, we can do this here. We obtain that Kp is num of S divided by den of S divided by 1 plus num of S divided by den of S. Or we can rewrite this as num of S divided by den of S plus num of S. And therefore, what we are interested in is, when we want to compute the poles of the closed loop system, we're interested in computing the zeros of this guy. Now, if S0 satisfies den of S0 plus num of S0 is equal to 0, it is the same to say that 1 plus num of S0 divided by den of S0 is equal to 0. Or in other terms, that 1 plus kg, let me repeat, k of S0, g of S0 is equal to 0. Okay? So really, in order to find the closed loop poles, we are interested in computing the roots of this equation, or the zeros of this equation. Now, as it turns out, very often we have the following thing happening. Okay, k could be a real number. Okay, in other terms, a simple game. Now, under what conditions does that happen? Well, for example, because you write k of S is equal to k times some structure k0 of S, and this is like a fixed structure, and k varies, variable gain. In which case we look for the roots of 1 plus k of S times g of S is equal to 0, or 1 plus k times k0 of S g of S is equal to 0. So call this guy g1 of S, and we look for the solutions to 1 plus k times g1 of S is equal to 0. When k is scalar, usually positive, then this guy here is called the root locus equation. Why? Because we will very often be in a position where we let k vary from 0 to infinity, and we try and find the roots of this complex polynomial equation as k changes. Varying k from 0 to infinity allows us to find the values of k for which the closed loop poles have or are in a satisfactory position. We will study this right now.